Great. So, hi everyone. Super excited for this session. And today our topic is going to be improving language understanding by generative pre-training. This is just a very just a very fancy name for the GPT paper. You might like most of you might have used the Chat GPT, which is a more advanced version of GPT. So, and please let me know if you cannot hear my voice or it's too loud or something like that. Okay. So a little intro for people who are wondering how this relates to GPT is that this paper initially, I'm not sure which year it came out in. I don't know, I'll have to see. But yeah, when this paper came out, it basically introduced this model called GPT or generative, which is like short for generative pre-training. So then they basically released the GPT-1, which is this paper currently about, which is mostly all you need to know about the entire GPT family. Then came GPT-2, which had many improvements. Like it wasn't a new model, it was just an improved version of GPT-1. And then came GPT-3, which had some more significant improvements, but it wasn't very different from GPT-1. After that, the other one that you guys know, which is Chat GPT, is actually GPT 3.5. So then came GPT 3.5 and 3.5 code, and now we have GPT-4. So that's the entire family of GPT till now. So yeah, everything stems from this original paper. This is I think my most favorite paper right now, and one of the most fundamental papers in all of wait okay yeah, one of the most fundamental papers in all of machine learning right now. Yeah, so let's get started. So, as you can see, this paper is already quite annotated. That's because I did a literature study on this some time ago, so that will help us, have a little marker as we move along. But yeah, anyways, so what this paper essentially does is it kind of builds on top of the original the bird paper that we not the bird paper but the transformer paper that we read in our last session, where we explained, where if you remember I explained there are two different components. There was one smaller component which is kind of connected to one larger component. So the smaller component was the encoder and the larger one was decoder, and both had the input data streaming into it. So this paper, GPT paper, is actually the decoder part. If you take the decoder part and if you make necessary changes, you will have a very, very powerful model that can generate text. And that's one of the key fundamental, not one of, but that is the key fundamental driving force behind current NLP and large language model space, right? So just to be clear, from the transformer paper, we are only concerned with the decoder part, right? Okay, so let's just get started. If you don't know by the basics, I'm not sure if you'll be able to cover them in this session today. So if you want, you can contact Karthikeya for the recordings if you have them on the previous sessions for the transformer paper and the attention thing, like the whole attention mechanism. But yeah, let's just get started. So what do we essentially mean by generative pre-training? So there are two types of training, like two different ways of training a language model. First is pre-training, and the second is fine-tuning, right? Or task specific fine tuning. So pre what and you will see this in more than one places. So pre-training and fine tuning are there for BERT and all other models too that are not unsupervised like GPT is. Let me just add GPT here. Okay, so what pre-training means, and I think I've explained this in the last video as like last talk as well, is that we essentially train the model for so that it understands the general semantics and language rules. Okay, so like we train the model on a lot of language text data, and we sort of expect the model to understand how the language is structured and how it works. The fine tuning part, and so pre training is very general, right? You can use a pre trained model and then you can add a layer on top of it, and you then fine tune it for multiple tasks, many tasks. Fine tuning is task specific. So the only thing you need to understand is that pre training part, it's very general, and the fine tuning part is task specific, right? So, okay. So how this works is this paper, GPT paper, it shows both pre-training and fine-tuning, yes, but it's mostly concerned with the pre-training part because that's how you get the actual GPT. So for those who know the basics of ML and they understand the difference between supervised and unsupervised learning, GPT is actually an unsupervised model, at least the text generation one. So it's basically like an unsupervised machine learning model. By what I mean by that is you don't need labeled data for your model to train. So you can train your GPT model without using labeled data. You can just give it a bunch of text, any text that you come across. Even you can use this GPT paper and you can scrape the text and give it to the model. And then you will have a very good working model. And I'll explain how it works. It's a very elegant concept. So let's get started. So there you can see these two different markers. First is generative pre-training and second is discriminative fine-tuning. So what this whole abstract says is that there is a lot of large unlabeled text corpora. By that we mean, you know, a lot of unlabeled text data. So blogs, articles, Reddit comments, Twitter comments, and books and all that. These are unlabeled text data. They are just text data. So the authors used the decoder part of the transformer to model the or rather train the model on that unlabeled text data. So how we do that, we'll come to it a little later. But they basically use basically use two different methods. So they use the generative pre-training one, as you can see here. Wait, yeah, they use generative pre-training, and then once they have trained the model on a very big corpus of unlabeled text, as you can see here, they do discriminative fine-tuning for each specific task. So what do I mean by task? I mean things like classification or text entailment or question answering or semantic similarity. There are multiple sorts of tasks, and we'll get into that later too. So and that's basically it. And other than the previous approaches, what this paper does is that it uses the task aware input transformation during fine tuning. That means the fine tuning that we do for each and every task is not general. It is dependent on the very so basically the input transformation. So whatever data transformation we do to the input is largely dependent on the task itself instead of other approaches where it was general, right? And we'll get to it how this happens. Actually, this is described all the way down here. I'm not sure where, but we'll get to that part later. So once we understand this, and then you can see the numbers of how well it performed. I'm not really into the numbers because they're already outsmarted now because this paper is very old by the looking at how fast this field is progressing. So I'm not paying much attention to the results because these results are heavily outpaced already. Anyways, so let's get started. So let me just explain the code. You can look at the paper and read it deeply, but let me just explain the core of how this paper works. So yeah, let's just read it through. So this paper uses a semi-supervised approach for language understanding using a combination of unsupervised fine-tuning pre-training and supervised fine-tuning. So the entire paper is actually semi-supervised, but the part that it's most interesting, the language generation part that I think most of you are more interested in, is basically unsupervised pre-training, right? And as you can see in this line, the goal is to learn a universal representation that transfers with little adaptation to a wide range of tasks. So what we mean by this line is basically, hey model, this is a lot of data. I want the entire model to learn the semantics of language, the rules. Let's say if it was trained on the English language, I want the entire model to learn the basics of English language. I want to learn what are conjunctions, what are vowels, what are consonants, and all that. And then once the model has all the knowledge of the English language and text and everything else, you can just use that existing knowledge for a wide range of tasks. So it's like teaching a kid the basic language using ABCD and then asking the kid to write a story, or asking the kid to complete a fill in the blanks exercise, or asking the kid to do anything. So kid doesn't have to relearn the entire English language for every task, right? if I am a child and if my parents are teaching me English language, I don't have to relearn English language for story writing and then relearn it again for fill in the blanks and then relearn it again for question answering, right? I will have to learn the language only once and then use my existing language for, or sorry, existing understanding for any new task with little adaptation or little changes. That's exactly how this model also works. So there are basically two stages here, and there is a two-stage procedure in this. The first is first they use a language modeling objective on unlabeled data to learn the initial parameters. So I'll come to this part later. That's the most important part in my opinion. And then we subsequently adapt these parameters to a target task using corresponding supervised objective. So the second part is basically the fine tuning part. The first one, the one in the pink, is basically the pre-training, as you can see in the label, right? And the one in purple is the fine tuning. So in pre-training, we learn what English language is, we learn everything. And in fine tuning, we use that understanding for any task. Okay. So yeah, so this, so now let's get to this other line. For our model architecture, this model architecture uses the transformer as we discussed in the last talk. The model choice, it's good because a transformer uses attention, which is really good at handling long-term dependency in text, right? So I think I explained this in great detail in the last talk, that why transformers are good and why they're far better than recurrent neural network. Because let's say if I have a long corpus of text, right? Let's say I have these all lines of text. An RNN, by the time, if you start here, by the time I reach like here, an RNN will start degrading in performance for generating the next word, because the way it handles long-term dependencies is by passing a context vector. So for this entire, so let's say we have this entire thing already and we want to generate the next word, this one, we will, for inside the RNN, will pass this entire text as a context vector v. Wait, we just paste this. Yeah, as a context vector v, and that v vector will be passed here. So all the important information of what happened before this word will be all comprised in one context vector, or maybe a few different context vectors, but that's not enough when we are dealing with large bounds of text. And that is the real problem. This is the reason why we actually don't use RNNs, why they don't work well, and this is why they have used transformers. We actually covered that in a great detail. So it uses attention, something called attention. Very interesting concept in all of in like recent machine learning, one of the most interesting concepts. So yeah, so it we use attention that handle long-term dependencies well, and yeah. So the next thing that we need to keep an attention on is how we give the data. So the data for this model, and I'll come to the details of the model, is basically text but tokenized, right? So this whole text we just give it to the model, all of it, right? But we tokenize it, and I highly recommend to anyone who doesn't understand what tokenization is, please check out what tokenization is. If not, I will explain a very basic version. When you have a lot of text, you take each and every word, although current tokenizers use something called subwords, so like something like EIMP, or maybe that's not a good example, I think. But yeah, so but right now for a basic example, we take each and every word and we assign a number to it, and that number is actually decided based on how close the word is to some other word. So for example, uh, let's say text and language, these are two different words, right? Text and language will have, maybe language, the word assigned to language will be, I don't know, this will be uh -1. There's no reason behind it. And text will be probably -2, because they are same, their distance is less. And if we take another word, let's say general, general is not close to either text or language, so the word assigned to it will be like 7 or 8. It's far. That's a very basic understanding of how tokenization works, and I'm probably like infringing on multiple concepts right now. But in essence, what you need to understand is tokenization essentially takes a bunch of text and converts it to numerical form so that a model can, do computation on it, because a model doesn't understand these strings because they're essentially represented as strings inside Python. Anyways, so as you can see, we do the tokenization, and the model uses structured text input as single contiguous sequence of tokens. So what we mean by that is single contiguous sequence of tokens is that, let's say we have 5,000 different files and all 5,000 of them are full of text. When we supply them to our model, we actually give them as not different files, but like all of it is just one single big chunk of tokens, text, which is tokenized. So big chunk of tokens, right? That's how it works. So yeah, it's now they do a like related, like pre-work analysis of other related work. I'll probably skip through this part because a lot of it I covered it in the last one about why LSTMs and RNNs are not that good. But yeah, if you want, feel free to just go to these citations and check the work out. Okay, the main part, the first one, which is the unsupervised pre-training. And I know some of you might be very scared looking at this equation, but it's actually very easy. So let me just first go and show you the model architecture so you understand what's meant by that. So remember I told you about the decoder part of the transformer. This is basically it. In fact, yeah, this is the decoder part of the transformer in a more simplified manner without the encoder connections, without the cross attention. So here we do text in position. Actually, our input goes in here. We do text in position embedding. Then we go to masked self attention. There is a skip connection which is added here, and then we do layer norm, 1 feet forward, another 1 feet forward, another layer norm, and then we can use it for either text prediction, text classification, or whatever, maybe text generation, text entailment, any n number of different things. So in essence, this is the model architecture. This is, and I think some of you will be able to appreciate how like rather simple it is for a model that can learn text in great details. So this number you are seeing here, wait just a second. The number this you're seeing here, 12x, it's basically how many of these blocks are stacked on top of each other. So I think this is like I think, yeah, this is the base GPT-1 model, which has 12 of these. And there is probably a table down below which shows how many tables are there, how many of these blocks are there. Let me see. Okay, no, maybe that's GPT-2 paper or something. Yeah. So there are multiple variants. There is a 12 of these blocks. There is one with 24 blocks. There is one with, I think, 36 blocks, all the way up to like, I'm not sure, 256 blocks, which is like a very big model. Or maybe I'm just missing the figures. But yeah. So this is the architecture of GPT. Very simple model. There's nothing, no big rocket science going on here. Now let's understand this. So when I talk about unsupervised pre-training, what I basically mean is that chat GPT type of model. You give it some text and it will generate after it. So of course, unsupervised pre-training is the name, or it's rather the process of how you train it. But if you just do unsupervised pre-training on a model, it's going to, the model that you will have at the end will be just like, I don't know, just like how chat GPT is, or for example, GPT-3 is. So this is the more interesting part of how it works. So yeah, let's get started. So remember I told you we have some tokens, right? And all our data is just a bunch of contiguous tokens. So let's say our tokens are T1, T2, T3, and so on up to, I don't know, Tn. N is the total number of tokens, right? Total tokens. So this is that. And but remember, one token, although there are multiple ways to tokenize text, currently there are subword tokens, but you can assume every token is one word. Okay, so maybe this is maybe this is like cat, and so on and so forth. So this is one, all of text decomposed in one huge collection of tokens. Now, when we pass it to the model, we basically like we pass it in batches or in small sections to the model. So we don't pass it as it is because you can understand it will be too big for the model to understand. And yeah, so okay, let me just focus on this equation first, so I may get backtracked there. So given an unsupervised corpus of tokens u1 and so on to un, we use standard language modeling to objective to maximize the following likelihood. Okay, what do we mean by maximize the following likelihood? Okay, this is the most important equation. What this means is that the probability that I'm going to get some token UI. And by the way, I was using T1, they're using UI, U1, it's the same thing. So I'm going to get some token UI given the previous token I minus K, I minus, I don't know, K minus 1, and so on up to UI minus 1 given theta. So what this means is, let me just break it down piece by piece. Yeah, so UI is the current token. UI minus 1 is the one that came before it. And for your ease of understanding, I'll use the word, right? So here token is basically a word, just so we can understand it better. So probability that this word came, this word will come next, given some word, like all these words that came before, and given the model. So that's basically it. So what do I mean by that? Let's take a very simple sentence. Okay, let's take this sentence. The first stage is learning a high capacity language model. Okay, this is our first sentence. How do I present it in this equation? Very simple. Okay, so probability that PUI, so let's say our I is 6. So what is 6? So 1, 2, 3, 4, 5, 6, right? So we are basically modeling a probability that we get an A, right? Because A is the sixth word, given we got the words from, I'm saying words from 1 to 5, right? So I want to find out what's the probability of getting the word A, given I had the first stage is learning words already, right? And also given the model. So we will basically give all the text to our model, and we want it to, and this is the loss function, by the way. This is how we calculate the model's loss. So we will give it the text, like let's say I gave the model this text: the first stage is learning a high capacity language model. And this is how the training will work. Okay, let me just erase it. Yeah, this is how the training will work. First, I will give the model just the, okay, then I'll ask the model to predict the next word. So of course, starting the model is going to be terrible, so it's going to predict something random which doesn't make sense. So I'll punish the model, right? I'll get the feedback, and then I'll give the model the and first. So I is equals to 1 and I is equals to 2. Then the model is going, and then I'll ask the model to predict what's the next word, which is the stage. And of course, the model may give a right prediction or a wrong prediction. Based on it, I will update the loss. Then I'll give the model the first stage and ask it to predict the next word, which is, and so on and so forth. And this is how the entire learning process works. So it's very simple. Basically, we have, so it's not really, I mean, I don't like to think deeply it as unsupervised, because all of our data has some intrinsic pattern, right? Unlike random numbers in a CSV file, text luckily has pattern. So we know that after our training will come no matter what. And after our training, procedure will come. And after our training, procedure consist will come, and so on and so forth. So this is how we do it. So this is why, let's see, even if I have just one single paragraph, and if you're good with probability and permutations and combinations, you can calculate how many different combinations exist, right? So maybe at one example will be is, and I have to predict the next word followed, and then is followed, and I have to predict the next word by. And maybe some different example is where we adapt, and I have to predict the next word, which is the, and so on. So this is how we train the model. And of course, you can understand that this is a very long stretch process. This is why the training of GPT is so memory intensive, and it takes so much of the time. Okay, so now you probably understand what UI means. I means, right? I is the current token. What does K mean? And what does theta mean? So I think if I'm not wrong, K is the context size, right? Yeah. So what do I mean by context size? Okay, if you have used ChatGPT, you might have heard of this thing called token limit, right? For ChatGPT, the token limit is, if I'm not wrong, 4097. What is this 4097? This is the number of tokens ChatGPT can, output at one point, or ChatGPT can look at before outputting something. So 4097 tokens, or that's rather for GPT-3, not ChatGPT, is the context length. It is the K. So it's very easy to understand what this is. So, let's take an other example. Let's say this is our training paragraph. Okay, let's say this paragraph is not the small. This paragraph has like 50,000 words. Okay, now if one word, if each and every word is represented by a number, any scalar n, and we have 50,000 plus 50,000, maybe we have like 100,000 numbers, it's going to create a lot of memory pressure, right? Because these are numbers after all. And if we want to train our model, let's say we did not have this k, so we'll have ui minus 1, ui minus 2, and so on up to ui minus whatever. We'll basically run out of stuff. So we'll basically run out of memory, not stuff, sorry. So in order to not run out of memory, we hopefully I'm not wrong here, but in order to not run out of memory, yeah, k is the size of context window. We assign a value k. So in very simple terms, if you don't understand any of this, just understand this. K will basically tell us how much do we look back into the past. Okay, let's take an example. Let's say this is some text training data, right? This is some training data, and let's say I want to predict the probability, or I want to calculate this L1U for is. Okay, and given the k is 12, so we have a context length of 12. So what this means is to find out, or maybe let's not keep it 12, maybe keep it like I don't know, 6. So what this means is if I want to predict the probability of is, we will only look at the 6 examples before it. So I'll look at 1, 2, 3, 4, 5. Okay, let's make it 5. Yeah. So I'll only look at like these examples. And this is how I will determine the probability. So I'll give the model adding auxiliary unsupervised training objectives, and I will ask it to find out the probability that next word is going to be is. I'm not going to include this word or this word or this word. They are not to be included because of course they are out of our context window. So this way, if you keep a smaller context window, every time you have to pass in something to the model, you will have less memory usage, right? Less than some, so we will not be running into OOM or out of memory errors. So GPT-3 has 4097K. So if we assume that every token is a word, which it isn't, but let's assume it is a word, every token is a word, then at one point GPT can, for predicting a text, GPT, or finding the probability, the GPT model can look at 4097 words before what comes before. And a very funny and coincidental thing is that 2 days ago there was a new large language model that was trained on the context length of 50,000 tokens. So now that language model can look at 50,000 words before it. That means it can generate something even bigger. You can give entire book to the model and it will give you a right output, which is currently impossible with GPT. So anyways, this is what the k means. So ui minus k all the way to ui minus 1 means that we only want to look into the small window. It's like a sliding window, if you understand that. So this is our entire text, and this window slides to the right all the time. Yeah. And what is this log p? So we basically want to calculate the likelihood, and then we want to sum it for all I. So let's say we have 50 or 500 examples. This will sum from u1 all the way to ui. So the L1 u will be the probability. Okay, so I hope this has made it a bit clear. Theta, if you don't understand what theta is basically the model. So what this crazy equation means is that calculate the probability of next word given this last k words, or last k tokens, context window tokens, and given the parameters of the model. So what, in all essence, what it means is that if I give this little boy to our model, what is the probability that I will get this word? Because at the end of the day, every machine learning and deep learning model in the world is just it's basically it's estimating a probability distribution, for the lack of better words. So everything in this universe, and this is what one of my teacher told me a very long time ago, is that everything in this universe is a probability distribution, real or imaginary, but it is a probability distribution. And everything you do, everything humans do or a model does, is just modeling a probability distribution and estimating the right approximate values for it. And that's what GPT does too. So yeah, that's basically the all of the essence of GPT. Now you have understand how GPT works. You give it some text, let's say I am, and it will work in reverse. So if you give GPT a text saying I am a, GPT will look at these three words and it will find the probability, and it will transfer these words through the model. So the model, which is GPT, it will predict some probability, right? It will predict that the next word is actually going to be uh, cat. So it will output cat. Depends on how well the model was trained. Okay. Now, if you don't understand how exactly it will predict a probability, you will actually have to look at the source code. The GPT uses a vocabulary. I think I told you that vocabulary is the list of all unique words or all unique tokens in our, or rather words in our text data set. And other than vocabulary, it will actually use something called an embedding table. Okay. And you will have to do a little bit of reading on this because it's a little out of our scope for today. But what an embedding table is that it's like a dictionary. Basically, it's like a lookup table for every word, and these embeddings are actually learnable parameters, right? So learnable parameters means that when we train our GPT model, these embeddings are learned. Okay. And I think you can see these embeddings, right? Text and position embeddings. So that's basically embeddings. Text embeddings is the embedding table. Position embedding is just a simple small array. So this will be our embedding thing. So when our model does give an output here for text generation, it's going to return an like a vector. And if you pass that vector to our vocabulary, it's going to output a word. So let's say cat or dog or whatever. So that's exactly how text generation, that's how GPT works in essence, right? So yeah, that's really it. Now let's go to the next one, which is, and you can do a reading of this. Let me just explain this equation to you too. So what this h naught wait, what the hell is that? Okay, yeah, what this h naught uwe plus wp means is that u is all the tokens or all the words, we is the weight of the embedding, or like, wait, where is it? Yeah, WE is the token embedding matrix, or as I told you, right, the embedding table, and WP is the positional embedding matrix or the positional embedding table. So we use two different tables here rather than just one. We use a token embedding and a positional embedding one. Let me use a dark color. Okay. So as I told you, these are learnable parameters. That means they have some weights. So this is WE, this is WP. So yeah, so we get this h naught. We basically pass our tokens through these embedding vectors. We get some intermediate representation h0. Then we pass that through one transformer block, hl minus one. Yeah, hl minus one for all I that belongs to one, between 1 and n. So there are like n blocks. In our example, we have like 12 blocks, I think. So we will pass that again and again and again. And at the end, we will apply a softmax, basically. Softmax, which is applied to the dot product of the output of the last block times the embedding matrix weight transpose. So WE transpose T, and this is how you will get the probability of every word. But this is, yeah, for the probability of every word. So essentially this thing. Right. And so this is the unsupervised pre-training part. This is how you pre-train the model. This is how you also use it for text generation. Now we go to the supervised fine-tuning part. So supervised fine-tuning is, let's say you train the model uh, using the above way. And by the way, if you're wondering what is the loss is actually, I think it's softmax cross entropy, right? So it, yeah, it's softmax cross entropy. If you're wondering how the loss is calculated, because I had this doubt, when you do this whole calculation thing, the loss is basically calculated as you have two copies, right? Let's say you give this text to the model, right? You give this to the model and you ask it to predict the next word, which is tokens. Let's say the model predicted something different. Let's say the model predicted, I don't know, lion, which is a which is very further away from what is the truth. In that case, you actually have the ground truth, right? You know what the real word is. It's tokens. So this is also y, which is your target variable, and lion along with all these text is basically a y hat or the predictions, and you put that all into softmax cross entropy or cross entropy loss, and you will get your loss, and you can just optimize that loss again and again to get a better model. Okay, let's I did this on a very wrong place. I have to explain something else here, but anyways, yeah. Okay, let's understand the supervised fine tuning. So now we have a model. Good God, what is this? Yeah, now we have a model that's trained on all of this stuff. And okay, wow, this is not going for some reason. Yeah, and what I want to do is use these model weights for something else. So by something else, I mean I want to use them for any other task, like classification. So what happens in classification is I give some text and I have some labels. This is, by the way, the supervised part of the training, right? So I have some text, or rather semi-supervised, not totally supervised, but semi-supervised. So classification is, by the way, completely supervised because you have some like examples and their corresponding labels. So you give text, you whatever text you have, and then you also have a corresponding label. Let's say 1 means the text is positive sentiment, 0 mean the text is negative sentiment. Sorry. So we give that all. We add these two tokens, which is the start token. Start token looks like that, or you can represent it in any way, and the extract token, which is, you can think of it as the ending token. So it will tell the model, and the text is in between. So it will tell the model where to start and where to end. Like, what is the start of the text? What is the end of the text? We pass this one example to the transformer, this bit, and then we add another linear layer on top of it. And that's how classification works. That's just another basic model. Now let's see entailment. So if you don't know what entailment means, it basically means that you have something called a premise and a hypothesis. So let's say, and there is an explanation on how it works, and you can read more detail about it. But since we're a little short on time, I'll basically explain what it is. So let's say my premise is, let me think of a good example. God will make good people rich. Okay. And our hypothesis is that I got rich after donating money. So what we have to do is we have to take a look at the premise, and we'll have to see if the hypothesis verifies the premise. So this is the case of positive entailment. There is also negative entailment. There's, I think, also neutral entailment. I'm not sure. So this is what entailment is. So we will take a look at the premise that's provided here, and then we'll take a look at the hypothesis, and then we will pass it through the model to get if it's positive or negative, or however we want to model this thing. So that's text entailment. Then we have similarity. I think it's pretty similar. We have some text t1, we have some text t2. We want to see how similar is t1 to t2. So first we'll split both of them into two examples. First we'll give t1 first, t1 before, and then there is a delimiter, which is basically like a separator. So start token, separator token, or maybe not a separator, but the token I think they use in this paper is a $sign. So by the way, these tokens are just to tell the model that these are two different things. They don't have any deep significance other than that. Don't get confused on this. Okay. So we'll first give text t1 here and t2 following it. Then we will have text t2 here and t1 following it. And we will give both of them to two transformers. The result is added, and then we pass it through the linear layer, and we get some, I think it will give you some number of how similar they are, or if they are similar or not. It depends on how you train the model, or I'm not sure what it does because I haven't like read the similarity part of it. But yeah, and I think multiple choice is quite easy for you to understand. We have some context, we have some answer. The context is same, and there are multiple answers. You pass all that through the model, and it will tell you what is the probability of each answer to be correct. And the one with the largest probability, highest probability, the answer will be the answer. So these are the the fine tuning phases. Now let's get back here. So I think you can understand this equation already. We actually saw it here. It's the same as the last layer equation. We also have like, and this is the same modeling thing as above. The key thing to note here is that we have another objective or another loss to minimize, which is this. So if you see L2C is basically somewhat like this, but the other one is lambda times L1C. Oh wait, no, that's different. Yeah, sorry. So L1C is different and L2C is different. So basically, one loss in supervised fine tuning is seeing the model's performance. The other one is seeing how well it is performing on that task. So one is seeing how the model is performing overall. This is how I'd like to understand this, and the other one is seeing how it's performing relative to the task. And we take both of these losses L1 and L2, and then we make another loss L3 where we multiply L1 by lambda. So I think this is like a, yeah, this is a weight lambda. So we multiply this by lambda, and yeah, we basically do the optimization based on the L3 loss. And I think we explained this. And okay, this one, yeah, this explains the start and end token. So this is the start token, this is the end token. And we also this paper also like here explains how they work around with text entailment and similarity. So that's basically all of the core essence of GPT paper. There is also detail on how much data it was trained on. So as you can see, GPT-1 was pre-trained on 7,000 unique unpublished books from multiple genre, including adventure, fantasy, romance. Uh, it was also there was I think another alternate data set which is like 1 billion word benchmark thing. Yeah, and this is the model specification. This is the 12-layer decoder thing. I think everyone should take a look at this. They also say what tokenizer they're using. So they're using FTFY library to cleaning the text, and then they use Spacey tokenizer. And after that, there are like fine-tuning details. So yeah, that's basically it. Then there is like other comparison, but again, as I told you, I'm not going over the like individual results because they are probably outdated by now. But yeah, this when this came out, this was really great state of the art, and you can actually code this thing by yourself too. It's not that like long of a coding session thing. So yeah, that's basically it. If you guys have any questions, please let me know.
That was really great, Tanay. And we have a question from Purva.
Yeah, sure.
What will be the sequence of words as in the is UI minus K and other words are followed subsequently?
Okay, right. I think what Purva is asking is how will you pass in the words? So if I want to calculate the probability, let's say this is a sentence, right? And I want to calculate the probability of getting off. I think I will give yeah, that's a smart question. I think if it's U minus K and U is or wait, was it U or UI? I think it was yeah, it was ui minus k, right? So I minus 1. So I think we will give it the closest word first. So I think we'll give numbers increasing transfer of effect. I'm still not sure on this. Maybe you can clarify this doubt with me too, because I haven't read this paper in a long time. But yeah, I'm not sure if it matters as much. But I think when I coded this from scratch, you would give the words like that in the order so that you give the model the sentence starting from the context length so that you have it. And I think this is what it is. So ui minus k is it. So you first give effect of transfer increasing number. So yeah, this is basically the order of how you will give the words.
Another question from Purva. What is the difference between the two vectors and what is the significance of using both? Is it for accuracy?
uh, Two vectors. I think I'm assuming you mean the positional embedding and text embedding, right? Or which one are you asking for? Is it for text
Yeah.
and positional embedding? Yeah, okay. So I actually explained this in the last paper discussion. Let me explain it like quickly. What text embedding does is I mean you kind of it will basically give you a vector over how the text is represented in a latent space. So in an, I don't know, 756 dimensional space, how it is represented. I really suggest you to learn about the text embedding. It's a very interesting concept. That's what text embedding is. It basically kind of puts each and every word in a vector space based on the distances. So if two words are similar, they will be close in the space. And if it's different from a third word, that third word will be way different, like way somewhere else in the space, in that vector space. The position embeddings basically tells us what like the positional significance of the vector of the word. So let's say we have this sentence, right, followed by a linear softmax layer. If we just pass in the model all these, all these weights of every word, if we pass in the model of every single weight, it's not going to understand what's the significance of layer before after softmax, or by before a, or other examples like that. So positional embedding will basically positionally encode what's the significance of the position of that word inside the sentence or inside the text we are feeding in.
One question from Dark Soul. So I just want to hear your opinion over something. As we know, like the GPT is decoder style LLM, which is great for text generation, and there is also a model named BERT, which is encoder style LLM, which is great for text classification. So BART is like take best of both worlds. It combines of the encoder and decoder, which I think is much great for text generation. So would you say that will be the industry standard for the future LLM?
Okay, I think there is like a different way to approach this problem. For text classification, see, if I view it as two separate problems, I would, if I were you, I would always go for BERT or some other supervised model, because they were basically trained like that. Okay, so you should take a look at how BERT is trained. There are two things how it's trained. It is also like trained using pre-training and then supervised fine-tuning later on, right? The same thing like GPT. But in its pre-training phase, there are two things. One is called masked language modeling, and the other is called next sequence prediction. So the way I look at it, I think BERT, and BERT is very outclassed right now, anyways. But BERT is actually far better in my opinion, and I would use BERT for fine tuning a model for text classification. GPT, I would, or any sort of GPT, I would only really use when I have to do summarization or I have to make, do text generation or something like that. So I'm not sure what the industry standard is, pretty much because like different companies with different use cases and different data sets have different industries, like different preferences. But go for a supervised model if you want to do text classification. That's my advice.
I think that's it for today. Thank you, Tanir, for being here. Any last words from you?
No, that's about it. Thanks a lot, guys, for attending. I hope I did try my best to make this as clear as possible.
Thank you everyone for joining. We will be back again with another session.